And hello everyone, this is Fei. In today's webinar, we're going to discuss how to train the neural networks with hundreds of GPU on our new system, Cedar and Graham. So what is the first topic I want to discuss is what's new. And I will cover hardware and the software updating, and also will give you some information about the details of the hardware and the softwares. And also in this webinar, I will tell you how to choose the place to run your job, because you may already know that we have different node types on the new machine, and the different node types enforce different scheduling policies. So I'm gonna say a little bit more about the node types and the scheduling policies here as well. And when you do the large-scale machine learning or deep learning stuff, you probably want to use more than one GPUs. So in order to use more than one GPUs, you need to find a way to manage all of these variables, or you call parameters, because you need to communicate between GPUs or between CPUs. So there are different methods for doing this, and I will discuss a little bit more here, and I will focus on the parameter server and the replicated way. And also, I'll give you some guidance to choose where to store all these parameters. If it's better to store in CPU memory, or it's actually better in the GPU memory. And next topic I want to discuss today is the interconnection, because, well, we do have multiple GPUs within a node. You don't need to worry about the interconnection networking stuff, but the maximum number of GPUs we have in a node now is only 4. So definitely is not many GPU enough for doing a large scale neural network. So if you want to train a real big model and you need to train that with multiple nodes, then you have to consider the interconnections and what's the topologies, network topologies with these nodes, and what's the protocol you need to use if you're using TCP/IP or using the InfiniBand IB protocol. And also, when you do a multi-node or multi-GPU training, and you need to worry about the speed of loading the data, because I/O will easily become the bottlenecks somehow. So I will introduce more about the I/O issues later. And at the end, I will, if we still have some time, I will give you some examples of how to run Caffe2 and Tensorflow on multiple GPU nodes. Okay, let's move to the first topic today. New systems we have right now, and we have Graham cluster, which has the Pascal P100 GPU 12 gig version, and there are 320 of them and 2 GPUs in the same node. And we also have Cedar cluster, which has most of the GPUs are P100 12 gig version, and we also have some P100 with 16 gig version. So in total, there are 584 GPUs, and on Cedar, there are 4 GPUs per node. So both Graham and Cedar are suitable for single GPU, multi-GPU, or distributed type of work. And we also have one IBM experimental box called Minsky, which equips the Pascal P100 with the NVLinks. So we only have one of this box in Sharcnet and 4 Pascal P100 NVLink GPUs inside. If you are interested in doing some experiment with NVLink, please feel free to contact us to get access to this machine. And softwares are basically, we support Caffe2. Well, we don't have Caffe1 installed so far because I would recommend everyone to use Caffe2 instead. It would be very easy if you have Caffe1. If you have models trained by Caffe1, there is a tool that you can convert your Caffe1 model to the Caffe2 version. And Caffe2 support multi-GPU and distributed training as well. And of course, we have TensorFlow. And Theano, we have the new Theano backend libGPU array library installed on the cluster. So you can use the libGPU array to build your PyGPU library, and then you can install Theano by yourself. So we also have Torch installed. And beside this software, and you can, some other software like PyTorch or some other tools you can always ask or you can install by yourself. So you will find more information about the softwares in the page I posted here. There is an AI and machine learning wiki page in Compute Canada wiki. So, but it's under construction, and we'll put more information in it. All right, so let's move to the next topic. It's about all the details about what's the difference between all these node types. So first, I'll go for the Graham GPU node, which is very simple configuration. That we have a dual socket CPU, 32 cores in total, 128 memory. And we attached 2 GPUs in the node, each GPU to each socket. So the interconnection between these nodes are InfiniBand FDR, which can reach a speed of 56 gigabits per second. And we also have the 1.6 terabytes NVMe SSD for faster data loading. And all the Graham GPU nodes accept single GPU jobs and the whole node jobs. For requesting this GPUs, you should add the slurm command --grass equal GPU, and you put the number of GPU you want. The maximum number can be 2 because there are only 2 GPUs per node. Okay, so let's move to Cedar. Cedar has 2 different GPU nodes. So the first one is base GPU node. It's still a dual socket, 24 cores in total, but compared to Graham, Cedar has 4 GPU each node. So you can see this graph showing that you have 2 GPUs attached to every socket. So basically GPU1 and the GPU2 has a connection to the CPU1, and GPU3 and the GPU4 has a connection to GPU2. Well, they share the same uplink, 16 lanes PCIe to the CPU socket. So the interconnection between Cedar nodes are Intel OmniPath, which can reach a speed of 100 gigabits per second. And there is a SATA SSD, which can provide you 800 gigabytes capacity. And Cedar-based GPU node accepts single GPU jobs and also the whole node GPU jobs. So you can request up to 4 GPU when you submit a job with Slurm. I mean, this 4 GPU here is 4 GPU per node. Okay, so another GPU node type on Cedar is the large GPU node. This is the best place for doing machine learning and deep learning. And it has the same CPU configuration, but more memory. And the GPUs there are all Pascal P100, a 16 gig version, which will give you a bigger memory capacity that you can run a bigger model on the GPU. And all these GPUs are under the same CPU socket and under the same PCIe switch. You will notice that the 4 GPUs under the same switch but shares the one app link to the CPU. And Cedar large GPU node accepts whole node jobs, and it also accepts a single GPU jobs less than 24 hours. That means you can ask one GPU on this large node, but it can only run up to 24 hours. Well, I think it's a reasonable policy, because if you're doing machine learning and deep learning research, you're testing your model, and you can test your model for a couple of hours and do some modification and testing again. Once you make sure that your model works, it can be parallelized on multiple GPUs. Then you don't need the single GPU job. Then you submit the whole node jobs after you did some modification on your models. Okay, so the unique setting here is that if you want to use this large GPU node, you have to specify LGPU when you ask for the GPU resource. So it's not the same as the base node. You just say, okay, I want a generic resource equal to GPU. And so here you need to specify GPU and also LGPU. So ask for this large GPU nodes. Okay, so all right, let's move to the next topic. It's very important here. So the different method of managing variables. Well, for parallelizing deep learning, machine learning models, or deep neural networks, so you can choose different ways. So the first is doing the data parallelism. That means you train different data batches on different GPUs, and you average the derivatives, or you average the updated parameter, and then you synchronize or update the parameter in the synchronized or asynchronized way. That is running. You can run this as a parameter server model. That is, you have a parameter server hosted somewhere in CPU or GPU, and you got a multiple workers then to train different data, different size of data, and the worker will communicate with the parameter server to exchange the gradient updates, and average. The server will average and update the final gradient, and then put the parameters and put them back to the worker. Then you can go next iteration and next iteration. So this is very basic parallelism model here. So then we have a question: is that where should we put these parameter servers? So should it be in CPU or in GPU? Well, that depends. You have to understand the bottleneck for the different node type. So if you take a look at the graph on the left, which shows the Cedar base GPU node, you will notice that the bottleneck will be the communication between the GPUs from different sockets. Because you will see that two GPUs, GPU1 and GPU2, share one PCIe link to the CPU, and only share the QPI bus between CPU1 and the CPU2. So that means you have two GPUs share one link to another side of two GPUs on the other socket. So this topology is good for CPU as server, because you get a more bandwidth between CPU and the GPUs. So you can put your parameter server on the CPU side, and do the operations like averaging the derivatives on the CPU side so that it can be overlapped with the GPU training. And this basically means you train your model on the GPU at the same time you push the gradient or push the update to the CPU, and this at the same time CPU is doing the averaging or anything you want to apply, and then put the updated gradient, updated parameter back to GPU part. So they can be overlapped with GPU, between GPU training and the parameter updating. And if you take a look at the right picture here, which shows the large GPU node, you will notice that you cannot do this CPU as parameter server because the bottleneck is between the GPU and the CPU. On the left, in the base GPU node, you got two GPUs share one link up to the CPU, but for the large GPU nodes, the picture on the right shows that you have all four GPUs sharing one uplink to the CPU. If you have the parameter server on the CPU side, the only one uplink will be the bottleneck. Then a better way to do is to have the parameter server in the GPU. So all the communication happens between GPUs and via the PCIe link. There is no need for the CPU memory to be involved. So for the large GPU node, then you will notice that you will get a better performance if you set up your parameter server on GPUs. There is another way to do this, managing all these parameters, and is that you can have the replicated parameters on all GPUs. So especially when people are doing synchronized static gradient descent, if you do a synchronized way, then you can have all your parameters stored in different GPUs, and then you do an all-reduced type of operation to sum them together and do the average on each GPU. So if you're doing this, and the total bandwidth between GPUs really matters. And that's why the large GPU node is more suitable for this type of model or parameter managing method, because the large GPU node has the highest total PCIe bandwidth. So if you take a look at the picture, then you see they're all under the same PCIe switch. So nobody's sharing the PCIe link with others. So if you communicate with from GPU 1 to any other GPU, then you get a full PCIe link. Okay, so NVIDIA provided a very useful and easy use tool called the NCCL, and a lot of software has it integrated, like TensorFlow, Caffe, and the Theano. They all have NCCL integrated in their package, and you can call NCCL function to do this all-reduced type of operation. Well, but NCCL is not always the best, because NCCL is highly optimized, but not for all sizes of data. NCCL usually perform better with a big data set, data with a big size. And if the data you want to exchange every time is very small and tiny, you will notice that calling an NCCL function actually takes longer time than you actually passing the data around. So I would highly recommend you to do benchmarks. And before we move to the next topic, talking about the interconnection, I want to show you some benchmarks here, and to get you familiar with all these different methods of managing variables and how they perform on different type of nodes. here is the Google Sheet I share now is for doing the benchmark on different type of GPU nodes. So if you take a look at, I tested the multiple models like a residual network, ResNet 50 layers, ResNet 152 layers, GoogleNet Inception 3, AlexNet, and VGG. Okay, so the first one is doing the Cedar large GPU node, and I tested different method of managing this variable. So you will see we got a parameter server, parameters in CPU, parameters in GPU, and also the replicated one with NCCL enabled and with NCCL disabled. So you will notice that the number of speed up, I put it in red. That is the best number I can get from all the different methods. So for the GPU large node, then you notice that if you're doing the replicated way with NCCL off, then you get the best performance on ResNet and the GoogleNet. But for AlexNet and the VGG, then you will get the best performance when you have NCCL enabled. So the reason why here I explained that is because if you're training the ResNet and the GoogleNet, they have for each layer they have fewer parameters to be exchanged, but they got multiple layers. That means you have multiple function calls, but each function calls it moves only a small amount of data. Like I said, calling NCCL takes some time. But for AlexNet and VGG, you have very big fully connected layers. That is like hundreds of megabytes of data. So you call NCCL only once, and it works on hundreds of megabytes data. So they give you the best performance because it's highly optimized. But you don't find the that big fully connected layer in the ResNet or in the GoogleNet. So, well, I would recommend you to do your own benchmark with your own model and try to find the best way to handle these parameters. Because you will see that for a Cedar base GPU node, you get the best performance when you have the parameters when you use the server parameter server model and also have the parameter in CPUs. Like I said before, and the bottleneck is between GPUs, then you can store the parameter in the CPU and overlap the communication and the computation. But you notice that the parameter server model in a CPU only works with the ResNet or GoogleNet. Well, the reason why is that training ResNet and GoogleNet takes a long time, and it takes long enough time for you to overlap the computation and the communication. So it shows a good result. But if you take a look at the result of the AlexNet, so you will notice that for on a base node, AlexNet doesn't scale very well. But if you take a look at the large node, well, it's still not that well, but it's much better than the base node. The similar thing for the VGG models. That you notice that you only get 3x improvement, but you have nearly 3.5 on the large node. Okay, I also have some other tests on the Graham GPU nodes. Graham GPU nodes shows the very similar performance compared with the Cedar base node because they all the GPUs are evenly distributed under different socket, and they got a bottleneck between socket. Similar things, so it's better to have the parameters in the GPU, not in the GPU, in the CPU side. I also have some benchmark for the IBM with NVLink version. So if you are interested, I can show you, send you the link later so you can take a detailed look. All the benchmark I showed you is only for training the neural network within the node. That means you use up to 4 GPUs. If you want to use more, if you want to train your model on the multiple GPU nodes, then you should think of the interconnection between the nodes. So the topology of the network topology on Graham and Cedar are the same fat tree topology, but the blocking factor is different. So the first thing is that you got non-blocking communication for 32 server under the same edge switch. So if you take a look at the server here, so in this level, so you got 32 server under the same switch. So 32 server under the same switch. That means on both Graham and Cedar, if you train your neural network on 32 nodes under the same switch, then they have non-blocking communication. If you go across these edge switches, if it's on Cedar, then you have 16 uplinks. So that means 2 nodes share one uplink to other leaf switches. That basically means that your total bandwidth will be reduced in half. And if it's on Graham, things is getting worse, that you only have 4 uplinks to other nodes. That means you only have 1 out of 8 total bandwidth. If you're doing the synchronized gradient design, then you probably want the biggest bandwidth, because you have to stop and wait for the communication every time you do this synchronized updating wait. But if you're doing the asynchronized way, it doesn't really that matters. So you can still use Graham to do that, and you can choose to have your parameter server have a multiple parameter server under multiple leaf switch. For example, you can have your parameter server here and another parameter server here. So you can have workers within the leaf switch to talk to the parameter server locally. And then you have the parameter server talk to other parameter server across this leaf switch. So that's some strategy that you can think of. Well, same thing for Cedar. You can do the same thing, or you can just say, okay, I don't mind using half of the bandwidth. It's fast enough, so I just do a synchronized way. Yeah. Okay, so that's basically for the blocking factors. And another problem here is the network protocol. So if you are familiar with the publication from Google or Facebook, then they use hundreds of GPUs training their neural network. You may notice that they are all training the neural network on their so-called cloud environment. So their cloud environment usually equipped Ethernet networking. That is different than the networking we have on our cluster, because their cloud or cluster is more for the customers doing cloud type of work. They usually use one node, or they don't need that much bandwidth between nodes. But our cluster is all HPC cluster, which equips bigger bandwidth networking interface than what we usually call it InfiniBand. So then you will notice that their program, like TensorFlow or Caffe, they usually developed for their own cloud and is using the TCP protocol. well, you can still run TCP protocol on the InfiniBand and by using the IP over IB, but the performance you will get is lower than the theoretical InfiniBand. So for example, the theoretical InfiniBand bandwidth can reach 100 gigabits, but if you do IP over IB on the Intel mini path, sometimes you get only 30 gigabits to 40 gigabits. So, but the different software, they provide some support for using IB directly that it will give you a higher bandwidth. Like a TensorFlow, by default, they're using gRPC, which runs on top of TCP protocol. And IB is also supported, but as third-party contribution. So they support IB through MPI or IB verbs. So Caffe2 currently is TCP only, but it has the ability to do IB. So the Caffe2 developers they're saying that IB will be supported in the future. But now, right now, because sometimes they notice that you don't need that much bandwidth to doing communication for some models like a ResNet, or GoogleNet. So 30 to 40 gigabits per second is big enough for this type of model. But if you define your own model that need more bandwidth, then you definitely want to use IB directly, not using the IP over IB. And PyTorch, similar. Now they use MPI and the TCP sockets, and later they will support RDMA using the IB verbs. Theano doesn't support, well, Theano itself doesn't support IB, but you can find some third-party project like Theano MPI that use the MPI to support communication using InfiniBand. And so if you're doing communication using the TCP protocol, and some things you have to keep in mind is that when they develop this software, they usually have a single network environment. So they pick up the default network adapter. But you have to keep in mind that on our cluster, Graham and Cedar, we have multiple network interfaces. If you run an ifconfig command, you will notice that we have Ethernet for managing all this node. We also have the IB for the high performance communication. So if you're using a default network interface or you're using the Ethernet, you probably use the very low speed interface that only achieve like a 1 gigabits per second. So you have to keep that in mind to always use the IB interface IP address when you do this TCP IP protocol. Okay, I will show you later how to find out all this in different interfaces and the IP address, how to pass it to the program. Okay, so before I move to the example, there is one more thing I want to talk about here is to the I/O bottlenecks. Like I already mentioned, that the I/O can easily become bottleneck when training with multiple GPUs. So if you train a ResNet 50-layer neural network on one TSCP 100 GPUs, and you can achieve a speed of 200 images per second. That's roughly 40 megabytes per second. So it's not a problem. 40 megabytes is not that high, but it's only for one GPU. So for example, if you have 100 GPU training this data, then you need a 100 multiply 40 megabytes per second. That is 4 gigabytes per second throughput. So we have different file systems. So like a project and scratch are all Lustre file system. It's network shared file system. And Lustre file system is able to achieve 30 gigabytes per second, but you need to use hundreds of the client to load a huge file, like a terabytes of files. It's not commonly seen in deep learning or machine learning because you cannot have that hundreds of the node to loading all the data at the same time, and usually you don't have that huge data set. ImageNet data set is only like 200 to 300 gigabytes, so it's not that huge. If you want to achieve that throughput, 30 gigabytes per second, then you need a few terabytes data. And if you have, for example, the ImageNet LMDB file that is 240 gigabytes, and if you load that data, you sometimes only achieve 300 megabytes per second. 300 megabytes per second means that it will be a bottleneck if you use 8 GPU. And that's for the continuous access. Because when you're training your data, you train it in a random way. So you pick up a random batch and then train it and put it into the GPU and then train your network. So random accessing is even slower. Sometimes it can be less than 100 megabytes per second, which basically means that you can only use 2 GPU. Any GPU you add more, any more GPU you add, you won't get any performance improvement because you can only achieve 100 megabytes per second data loading. So then we have a solution to this is to use the local file system, which is in /local scratch. So we have SSD-based local scratch, 800 gigabytes on Cedar, 1.6 terabytes on Graham. So Cedar equips SATA SSD that it can run up to 500 megabytes per second, and Graham has NVMe SSD, and the speed is more than 1 gigabytes per second, and sometimes they achieve 2 gigabytes per second. So it will be fast enough for loading all this data because each node has their own local scratch. That means 4 GPUs share one SSD that has 500 megabytes per second. That is high enough for 4 GPU to share one SSD. But there was some limitation for this, is that you have to copy the data every time before your training start, because the local storage will be cleaned after job is finished. So anytime you have a new job on this node, you need to copy them over. And I highly suggested to copy the data to local disk for faster random access, because the SSD is good for doing this random access. So original data can be stored on multiple OST on project and scratch to achieve higher throughput. I'll explain more on the next slide in what is the OST. So a Lustre parallel file system looks like in this way. So you have compute nodes and trying to access data from the OSS. It's called Object Storage Server, and each OSS has multiple OST. So by default, a single file is stored in a single OST. So if you have multiple compute nodes trying to load the same file, then the bottleneck is that you have single OST, and the performance of a single OST will be the bottleneck if you have multiple nodes loading the same data. But you can choose to strap the files across multiple OST, so it will give you a higher throughput. So it would be very easy to do this. I showed some command here. So you will see that you do a Lustre file system, LFS strap. And for example, I set the 8 OST, and then I copy my previous file to this newly created file. and after that I will check the file just to make sure they are strapped across different multiple OST. Then you usually get a better performance when you load the big data file. Okay, let's move to the last one. So I'll show you example. So before I show you the example, I just show some common problems here. So the first problem is what machine learning deep learning tools are available. Like I said, TensorFlow, Caffe2 available, and Theano is available with libGPU array. And we have Torch available, and the PyTorch can be installed easily. You just do a pip install, get it download from the internet. And in the example, I will show you how to require hardware resource using Slurm, and how to launch the program on all nodes. Well, if it's MPI job, it's very easy that MPI handle all this. But like TensorFlow, if you by default in Caffe2 is not MPI supported, so you need to find a way to launch all this program on each node. And also, I will show you how to use the local storage and how to get the correct IP address. The example I want to show you here is the Caffe2. So Caffe2 is available as a modular. So if you do a modular spider Caffe2, then you will notice we have Caffe2 0.81 available. So in order to use that, you need to load CUDA GCC modular first, then CUDA modular, and also the cuDNN modular and the Caffe2. So the modular command will switch all the modular to. So if you do a modular list, you will see I now have all this modular loaded. Okay, so I'm using the example a ResNet 50-layer model as example. So let me show you the submission script first. So let's take a look at what's inside my submission script. Okay, so this is basically a Slurm submission script, and I have account set, job name output. The memory I asked for 250 gig because it's on large node. And I asked for 8 nodes for my job, and number of tasks. You have to set up this number of tasks per node because it will tell Slurm how many program to launch each node. If you set the number of, like I said here, number of tasks per node equals 1, it will launch 1 program. Well, my program is a Python script, so it's actually running 1 Python each node. And I also set the CPUs per task equals 24. 24 is all the cores, because the Caffe2 and also TensorFlow, they take advantage from multi-CPU thread. So they use more CPU threads to load the data and try to do some pre-processing, and also you need 1 CPU core to control 1 GPU. So usually you will notice that the Caffe2 will use like 8 to 10 CPU cores each node. And also the time limit I set to 3 hours. Okay, so the first line you will notice that is the rsync command, that what I'm using here to move the data from scratch to local scratch. So you notice that I used S1 to launch this command because I want this as rsync to run on all nodes. So because I said number of tasks per node equals 1, if you run S1 rsync, it will run 1 rsync command each node. So this rsync is basically copy from scratch my username, the data is ImageNet data set, to local scratch my username, Slurm job ID. Here is the very important thing is that the local scratch space is created with job. So each job can only access the local scratch within this space. I mean, the Slurm, there is a folder created after you launch the job, that the folder will be placed under the local scratch, your username, with the Slurm job ID. So this environment variable that will give you the Slurm job ID, then you can locate where the folder is. So once you execute this srun command, and it will launch the rsync on all nodes and copying data at the same time from one place to the local disk, each local scratch. And the second command I show here is to actually launching the job. So I'm still using srun because I want this Python code to be run on all nodes. I need to specify this LGPU again here. I'm not quite sure why, because I have already asked in before, but it looks like the Slurm needs you to put it into it to use this resource. I'm not quite sure if it's a bug from Slurm or not, but you need to put this flag after the srun. And srun Python, so I got some flags to put into this code. It takes the training data place. So you need to notice that this here, I'm using the local scratch. So for all the nodes, the path to the file is the same because all the nodes has the same Slurm job ID. And you specify the GPUs to use. Well, this script runs on the local. Well, I mean, run on the one node. So from one node, you can only see 4 GPUs. Then you say, okay, I'm this node, and I want to use all the GPUs, like 0 to 3. And the batch size here is the node batch size. We have 4 GPUs. Each GPUs I want to use 32 images per batch. So in total is 32 multiplied 4. It is 128. This is not the whole batch size, because the whole batch size should be this batch size multiplied by the number of nodes. So, well, it's something in your code that you can definitely define. And the next important thing here is the number of shared server. So this number of shared server is basically the number of nodes. You can get this number of nodes number using the Slurm environment variable, Slurm job number of nodes. Then it's being put into all the commands that run on all the nodes. And also you need the run ID. It's something like a unique ID, and you can use Slurm job ID as this unique ID. So I'm using Slurm job ID here. Well, you can use others, but you have to make sure that all the nodes runs the same command, get the same value here, because they need to be able to run with the same run ID. That's how they communicate. And set the number of epoch size, file store path. So file store path here is that Caffe2. So Caffe2 use, well, you have 2 options to run in Caffe2. So the most common and the default one is to have all this node information stored in a file. So that basically means all this command run on different node will write into a file showing that, okay, so I will write my IP address there. Then you know, oh, what my IP address is there. So this place is basically shared. It has to be in a shared file system. So it can be Scratch, it can be project, it can also be home. It must be shared by all the nodes. It cannot be a local. And if you're familiar with this Caffe2 multi-GPU training, you will notice that I missed one very important flag here. It's called shared ID that is needed for distributed training. So shared ID is basically a unique ID for each node. That's basically from 0 to whatever, how many nodes you use. So, well, there is a Slurm variable called a Slurm node ID, but you cannot put Slurm node ID here because this srun command is actually runs on the master node, or you can say this is the node that launched the job. So if you put the Slurm node ID here, you will put the same number for all the programs running on a different node. So in order to pass a different value into this flag, you can put the Slurm node ID in the code. Okay, let me show you how to do this. So this is very important. This is not only for Caffe2, it also for all the other framework, like your TensorFlow. You need to put some unique ID, or you put the unique IP address. So that's something you have to think about. That is, when you run this srun command, it actually runs on the one node that is the master node, or is the initial node that you launch all this program. So this Slurm environment variable, you can get this. You should get this Slurm environment variable on each node, not on this master node. Okay, so if you take a look at the code, I did some modification here. So it's very easy to get all this information in the Python. So you can just do, this is very easy. You just run, because this Python script is executed on each node. So each node will run this script and get a unique value from the Slurm node ID. Then you put this Slurm node ID into your flag manually. So like I do here, so I put the shared ID with a default value of node ID. So that means basically I passed a unique ID to different node. Okay, so that's basically everything in my code, and I can show you some output samples that I noticed. I submitted a job yesterday, and let's see some output examples. So this output shows the training on the single GPU. Then you will notice that the single GPU achieved the performance 180 images per second. So I got another job submitted that is using the shared file system. Actually, I put all the file in the Scratch space. Then you notice that you achieve only 200 images per second for 4 GPUs each node. This output shows the 4 GPUs. Then you see 4 GPUs is not giving you much better performance, because in this situation that the file I/O becomes the bottleneck. And I should have one job running here right now, and I got this job training on 8 GPU nodes. That is basically 8 GPU, 32 GPUs. So let me show you the output. All right, so the output shows, now you notice the performance here is much better, and you've got a 500 images per second. This output is not for 8 nodes in total, it's for 1 node. So you can just, you need to sum them up. So if you sum them up, then you'll notice that you probably reach more than 4,000 images per second on 32 GPUs. And it's running very well because ResNet, the parameters need to be changed is very small. So the communication is not a big problem. So you have a very good speed up